All right, there we go. We're in business. So, like I said, I'm Suzanne Farrellock, and we're going to be looking at limits at infinity and horizontal asymptotes. Looks like some of you have already touched on this in your class, which is great. So hopefully this will just help reinforce what you've already learned in your classroom. Don't forget to follow us at Think5able on Twitter, Instagram, and YouTube to stay up to date on all the latest and greatest opportunities that Fiveable has to offer you. So in tonight's stream, we are going to look at limits at infinity, and then we're going to tie that back to end behavior and also connect it to horizontal asymptotes. All right, so let's get started. The first thing I want to talk to you about is the limit as x approaches infinity of x squared, and x to the fifth. So hopefully these are functions that you probably have a feel for what they look like. So the function x, for example, is just a line with a slope of 1. As my x values increase and get bigger and bigger and approach infinity, what is my function x going to do? Go ahead and comment in the chat. Awesome. Great, Megan. Yeah, so the limit of x as x approaches infinity is going to equal infinity. Okay. Similarly, if we think about that graph of x squared, a nice parabola, the limit as x approaches infinity for the function x squared is also going to approach infinity. Okay. And same thing with x to the fifth. As my x values get larger and larger and larger, so is my function. It's also going to approach infinity. So if we look at this, all three functions go to infinity. My question for you guys, though, is which function grows the fastest? What do you think? Yeah, awesome. X to the fifth. Great. Yeah, so I've got two Megans. Awesome. Yeah, absolutely. And I think to some extent, we probably have that intuition that x to the fifth is going to grow the fastest. But let's also go ahead and take a look at what that looks like in a little bit more detail. So if I look at x squared, and x to the fifth as functions, and I plug in 0, okay, all three of those functions, when I plug in 0, are going to equal 0. So at this point, we're tied. Let's go ahead and plug in 1. Same thing. They all give us an output of 1. Still tied. Okay. Let's increase that input value to 10. Now we see that x to the fifth is starting to take the lead. So we've got 10 compared to 100 compared to 100,000. Check out what's going to happen now if I plug in 100. Now we're comparing 100 to 10,000 to 10 billion. Okay. Now, if I plug in 1,000, now we're really starting to see a difference in those values between x and x to the fifth. It's really becoming significant at this point. So at large input values, the difference in x and x to the fifth is definitely significant at this point. We started out tied, and then x to the fifth was a little bit ahead, but not that much. But now when we input 1,000, that difference is big. And as that input value gets larger and larger and larger, that difference is going to become even more significant. Okay. So keep that in mind as we continue this conversation on the next slide. Anybody know who the richest man alive is right now? Any guesses? Or do you know somebody that has a lot of money. So Warren Buffett, okay, Bill Gates. According to my research, there's someone, yeah, that Amazon CEO actually is the richest man alive these days. His name is Jeff Bezos. And according to my research, he is worth $150 billion. Okay. So if you think about the situation he's in, if you have $150 billion, a single dollar or two is really going to kind of seem insignificant to that 150 billion. Okay, so that's kind of the same conversation we were just having in comparing x squared, and x to the fifth. At some point, those numbers are going to become so large that the smaller ones just don't seem to really matter as much. A dollar or two is going to seem like nothing to Jeff Bezos. Okay, so let's look at that now in terms of relationships, in terms of the relationship when we have limits that go to infinity. The first example I have for us is the limit as x approaches infinity of the function 5x cubed plus 7x minus 1 all over x squared minus 3. Now, keeping in line with that theme of the fact that smaller numbers become a little bit insignificant as we get bigger and bigger and bigger and bigger and approach infinity, when I look at this limit, the only thing that I'm really going to pay attention to is the term that grows the fastest in the numerator and the term that grows the fastest in the denominator. Because as my x values get larger and larger and larger as I approach infinity, the 7x minus 1, it's not going to have that big of an impact. The minus 3 in the denominator, it's not going to have that big of an impact. So what we're able to do here now is we're able to say that when I take this limit is actually equivalent to taking the limit as x approaches infinity of 5x cubed over x squared. Okay. Let's go ahead and reduce 5x cubed over x squared now. This would be equivalent to taking the limit as x approaches infinity of 5x. The limit as x approaches infinity of 5x is going to be infinity. Okay. Check out my notation too as I went through. A common mistake that many of my students make is they start to do the following. They start to here, let me show you. They start to leave off that limit notation. The limit as x approaches infinity of 5x cubed over x squared is not equal to 5x. It's equal to the limit as x approaches infinity of 5x. So be very careful as you go through and you're writing these limits that you're also very careful about your notation. Super, super important to make sure that you continue to write that limit notation. Okay. All right, let's check out another example. All right, let's see. Give me a second. This is what was happening to me at the beginning, too. That slide's not advancing for some reason. All right, let's try this again. I'm going to exit again and reconnect. Sorry this is happening. All right, looks like we're back in business. All right, this time I want us to think about the limit as x approaches negative infinity of 35x to the 21st minus 17x plus 21 all over 9x squared minus 55, okay? Now, we're going to negative infinity this time instead of positive infinity, but the same is true in terms of what's going to be significant in the numerator and the denominator. We still want to look at the term that's going to grow the fastest. So in my numerator, I'm looking at 35x to the 21st, and in my denominator, here we go. And in my denominator, I'm looking at 9x squared. All right, now that means that this limit as x approaches negative infinity is equivalent to 35x to the 21st over 9x squared. Okay. Let's simplify that just a bit, and that's going to give us the limit as x approaches negative infinity of 35, oh, now I went ahead and didn't want to, 35x to the 19th over 9. All right, so think about what's happening at this point. I am inputting larger and larger negative numbers because my x value is approaching negative infinity. What do you think is going to happen to 35x to the 19th over 9 when I input larger and larger negative x values? Go ahead and comment in the chat. What do you think is going to happen? Yeah, great, Karen. It's going to be negative. So this is going to approach negative infinity. So part of the reason that that's happening is because as I input larger and larger negative values, pay attention to the fact that in this particular problem now, I have an odd exponent. So keep in mind that as you take a negative number and raise it to an odd exponent, you're still going to get out a negative number. So this time, my limit's going to actually go to negative infinity. Let's look at one more example, okay? This time we have the limit as x approaches negative infinity of 5x to the 4th minus 2x plus 15 all over x squared minus 25. Okay. So just as before, I'm paying attention to the term in the numerator that grows the fastest, and I'm paying attention to the term in the denominator that grows the fastest. So this limit is equivalent to the limit as x approaches negative infinity of 5x to the 4th over x squared. Let's simplify that one step further, and this would be equivalent to the limit as x approaches negative infinity of 5x squared. Now, just as in the last problem, my x values are getting larger and larger negative. But this time, notice my exponent that I'm dealing with at this point is even, not odd, it's even this time. So what do you think is going to happen this time as the limit of as x approaches negative infinity of 5x squared? Go ahead and comment in the chat what you think will happen this time. Yeah, this time it's going to go to positive infinity. Excellent. So it's really important as you look at these limits at infinity to also pay close attention to what the function is that you're dealing with. Whether that exponent ends up being positive, even or odd, and whether we're approaching positive infinity or negative infinity plays a big role in what that final answer is going to be. Now, in the last 3 examples that we've done, I refer to these problems as top-heavy, okay? And the reason I say that is because the term in the numerator was growing faster than the largest term in the denominator. So I call these top-heavy problems. That's going to come back up later when we talk about the different scenarios that we're going to come across. So these first couple examples I presented to you were called top-heavy problems. Okay. So let's kind of formalize what we've discussed at this point, just with the top-heavy problems, okay? If I take a limit as x approaches infinity of f of x, that limit can approach positive infinity or negative infinity. So what this is saying is that my function can increase or decrease without bound as that x increases without bound. And similarly, as I take a limit of a function where my x goes to negative infinity, again, it might approach positive or negative infinity, okay? But these are the scenarios that you're going to come across, these two situations, when you have a top-heavy problem. And again, it's important to pay attention to what the function you're dealing with is in relationship to whether you're approaching positive infinity or negative infinity. Okay. So the next thing I want to look at, I've got to fill in the blank for you guys, so go ahead and comment in the chat. It says, when x is large, 1 over x is blank. So I've given you guys some numbers underneath there. 1 over 1 is 1. 1 over 10 is 0.1. 1 over 100 is 0.01. Based on that pattern, what are you observing that when x is large, 1 over x is what? Yeah, great. It's small. Any thoughts on how small it is? Yeah, I mean, it's really, 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 really small. It's basically 0. So if you look at this pattern that we've developed so far, I mean, I could keep going. And that number is getting smaller and smaller and smaller and closer and closer and closer to 0. So let's put this into notation. The limit as x approaches infinity of 1 over x is going to equal 0. So as my denominator gets larger, 1 over x is going to get smaller. And it's going to get so small, it's basically 0. Okay? We can make a similar argument for the limit as x approaches negative infinity of 1 over x. Okay? If I were to go back to my previous slide, every single one of these would end up with a negative. But again, because we're talking about it getting so small, really, really, really small, that it's approaching 0, it's simply approaching 0 from the other side, but it's still going to approach 0 itself. So the limit as x approaches negative infinity of 1 over x is also going to give us 0. So let's use this knowledge now that we've just gained about the limit as x approaches infinity and negative infinity for 1 over x to explore some other limits a little bit further that are similar but a little bit different, okay? So going along with the same thought process as in the beginning, anytime I'm taking a limit that approaches infinity or negative infinity, I'm really only worried about the term that grows the fastest in the numerator and the term that grows the fastest in the denominator. Okay, so I'm still looking at only negative 2x to the 4th in the numerator and just x to the 6th in the denominator. This limit is equivalent to the limit as x approaches infinity of negative 2x to the 4th over x to the 6th. Now, when I simplify this in the next step, and this is equivalent to the limit as x approaches infinity of negative 2 over x squared, we're in a similar situation now to when we had the limit as x approaches infinity of 1 over x. Because the denominator is going to continue to grow bigger and bigger and bigger and bigger, but that means the overall function is going to get smaller and smaller and smaller and smaller and smaller until it's basically 0. So the limit as x approaches infinity of negative 2 over x squared is going to go to 0. So the denominator is getting larger and larger and larger here, so that function negative 2 over x squared is going to go to 0, okay? Rather than calling these functions top-heavy, I like to call these functions bottom-heavy. The term in the denominator grows faster than that term in the numerator. So these ones are what I refer to as bottom-heavy. Let's check out another one. All right, this time we are approaching negative infinity. So we've got the limit as x approaches negative infinity of 5x to the 10th plus 2x over 8x squared plus 7x to the 9th plus 1. All right, in my numerator, what is the only term that I am going to consider? It's that 5x to the 10th. In my denominator, the only term I'm going to consider is that 8x to the 12th. And again, I'm picking those terms in my numerator and my denominator because they grow the fastest, okay? Those are the 150 billion Jeff Bezos compared to my measly little dollar, okay? So let's write an equivalent expression at this point. We have the limit as x approaches negative infinity of 5x to the 10th over 8x to the 12th. Keep in mind, as I mentioned before, notation here is super important. You've got to make sure that you're rewriting that limit notation because that's what keeps it equivalent. So now we've got the limit as x approaches negative infinity of 5 over 8x squared. It's bottom heavy. So that denominator is going to get larger and larger and larger and larger, which means that 5 over the quantity 8x squared is going to end up getting closer and closer and closer to 0. Okay, so anytime we're looking at these bottom heavy functions and we're taking limits that go to infinity or negative infinity, we're going to find that they approach 0. All right, check out this next example. This next example is the limit as x approaches infinity of 2x squared minus 1 over x squared plus 1. Take a minute on your own and see if you can solve this one. It's slightly different than the other ones we've done so far. So take a minute on your own. Once you think you've got that answer, go ahead and type it into the chat and we'll see if we agree. Yeah, Megan, Sonia, Tony, Sammy, great. 2, okay? So what is it that you guys observed was a little bit different in this problem than the previous ones? Yeah, great. So when I look at the term in the numerator that grows the fastest and the term in the denominator that grows the fastest, they have the same exponent. So when I go to write an equivalent limit here, I'm going to end up with the limit as x approaches infinity of 2x squared over x squared, but that's really just the limit as x approaches infinity of 2. I've got a constant limit here. So that means my limit itself is also just going to equal 2. So the significance in this example was the exponent in my numerator and the exponent in my denominator were the same. Okay. Megan, I'm just curious. What is EATSDC? Is that an abbreviation for something? Oh, okay, cool. I hadn't seen that abbreviation before. All us teachers have little weird ways of remembering sometimes, and a mnemonic device is a great way to do that. I love it. All right, let's try one more of these. This time I want to take the limit as x approaches negative infinity of negative 9x cubed plus 12x squared minus 9x plus 15 all over 3x cubed minus 5, okay? So hopefully we're getting the pattern here and the hang of this in terms of we're only going to consider the term that grows the fastest in the numerator and in the denominator. So when we check this one out, we run into the same situation where my exponent in the numerator and the denominator are the same. So this is going to be equivalent to the limit as x approaches negative infinity of 9x cubed over 3x cubed. Now, in addition to x cubed over x cubed simplifying here to 1, that negative 9 over 3 is also going to simplify to negative 3. So we are going to end up with a limit. Whoops, I forgot my negative infinity. Don't forget that. We're going to end up with the limit as x approaches negative infinity of negative 3, which is going to equal negative 3. Yeah, I love that saying too. Same over same, play the coefficient game. All right, so let's kind of formalize where we're at now with the last two sets of examples we've been looking at, okay? So we've now come across situations where we have the limit as x approaches infinity of f of x equals L. So what this is saying is that my values of the function f of x are going to approach the number L as x increases without bound. So we've been coming across the numbers where we had the ratio of the coefficients, and we've been coming across the functions that were bottom heavy, and those approach 0. Now, we also were looking at the limit as x approaches negative infinity of f of x, and let's say that it equals m. So this is saying that as my function approaches the number, or the function f of x, my function is going to approach the number m as x decreases without bound. So it's getting larger and larger negative. But what's important here is to notice that I made these equal different numbers. The significance here we're going to talk about in more detail in just a minute. But some functions are not going to behave the same at positive infinity as they are at negative infinity. So it's important to make that distinction here, and it's going to come up in just a slide or two, and it's going to be really important to us. Okay. So at this point, let's just kind of summarize where we're at and what we've discussed so far before we go on any further. Okay, we've essentially come across 3 scenarios with infinite limits. Okay, the first scenario was when we have a top-heavy function. So this is where the term in my numerator is growing faster than the term in my denominator. When I have a top-heavy situation, my limit is going to go to positive or negative infinity. Now, whether or not it goes to positive or negative infinity, we're going to have to do a little bit more investigation based on what that actual function is. But we're going to be able to write here that when it's top heavy, my limit goes to positive or negative infinity. Okay. The next scenario we came across was bottom heavy. So this is where the term in my denominator is growing faster than the term in my numerator. And in the bottom heavy situations, we found that the limit goes to 0. And my third situation was that the exponents are equal, or the term in the numerator and the denominator growing at the same rate. And in this case, the limit goes to the ratio of the coefficient. Does anybody have any questions at this point about anything that we've discussed before we move forward and start connecting this with some past material and some other connections with functions? I'm taking that as a no, but just to be on the safe side, go ahead and give me a thumbs up or a smiley face or something like that in the chat feature to make sure that I know we're ready to move on. Awesome, awesome, awesome. Okay. Good. I love it. All right. So let's take a couple examples where we look at this from a visual standpoint. Now, I mentioned to you guys in this previous slide, here we go, that my limits as x approaches infinity of a function might be different when it's approaching infinity versus negative infinity, okay? So that's what I'm really trying to push to you guys in these two pictures, okay? If I check out this graph on the left-hand side, the limit as x approaches infinity, let's call this graph f of x. The limit as x approaches infinity of f of x. So as my x values get larger and larger and larger, I'm finding that my function also gets larger and larger and larger. It approaches infinity. But as my limit of my f of x as x approaches negative infinity, where's this one go? What's the limit as x approaches negative infinity of this function f of x? Yeah, great, Karen, great, Hannah. So we're seeing that as my x values get larger and larger in the negative direction, that this function f of x is actually going to -4. Okay? So it's important to realize that there are functions out there that are not going to do the same thing as their x values increase versus when their x values decrease. Okay. Let's call this next graph g of x, okay? We want to look at the limit as x approaches infinity of g of x, and we also want to look at the limit as x approaches negative infinity of g of x. Okay. Go ahead and on your own, take just a couple seconds to decide what you think these two answers are, okay? And let's start in the chat with saying what you think the limit of g of x as x approaches infinity is. Yeah, awesome. Looks like we're all on the same page there. Okay. See what you think now about the limit as x approaches negative infinity of g of x. Awesome. Y'all are rocking it. So this one is going to approach -3. So again, just another visual example for you to see that the behavior of a function as x approaches infinity might be very different than as x approaches negative infinity. So let's connect this to some material that you probably learned about in pre-calculus, and that topic is end behavior, okay? Limits at infinity really let us formalize our discussion about end behavior using proper mathematical notation, okay? So if we look at this first example, which is a parabola, okay, we can now talk about its end behavior in using this limit at infinity notation, okay? So when we talk about end behavior, we're really just talking about what's happening to this function. Let's call this one f of x. As x approaches infinity, and what's happening as this function approaches negative infinity. So we are going to find that in both instances, my function approaches infinity here, okay? So depending on the content of your pre-calculus course or how in-depth this discussion went, some of you may have seen this notation in pre-calculus, and some of you, this function notation with limits might be new, but now hopefully you're able to see the relationship between the two and connect it to the material you're learning in calculus. Let's check out another graph. This time we'll call this graph g of x. Woo, we got zoomed in there. My limit as x approaches infinity of g of x, and my limit as x approaches negative infinity of g of x. What do you think the solution is going to be this time for my limit as x approaches infinity of g of x? Now, be real careful. Keep in mind that my x values are getting larger and larger and larger. So if we look at the end of this graph, okay, it's going to continue to go up. And as it goes up, it also moves further to the right. So as my x values are increasing, my y values are also increasing. So as I take this limit as x approaches infinity of g of x, my x values are getting larger and larger. My function values are going up. They're also getting larger and larger. So the answer here would be infinity. Okay. What do you think about that second limit, the limit as x approaches negative infinity of g of x? Yeah, great. This time we're going to negative infinity, okay? So as those x values get larger in the negative direction, my function continues to extend. Its y values are going to negative infinity. Okay. So notice some differences here. In that first example I gave you, we actually had some even symmetry, and so both of those approached positive infinity at the ends, where in the second function g of x, as x approached infinity, my function went to infinity, but as x approached negative infinity, my function went down to negative infinity. All right, let's look at a third example here. It's being difficult again. I don't know what's happening here. There we go. Okay. Let's call this one h of x. All right, I want to know this time the limit as x approaches infinity of h of x and the limit as x approaches negative infinity of h of x. Now, these two are actually going to end up having the same answer. What do you think that solution is? Yeah, great. It's 0. Okay. So if we follow this graph as x gets larger and larger and larger, my y value is getting closer and closer and closer and closer to 0. Same thing's happening over here. As my x values get larger in the negative direction, my graph is approaching that y value of 0. It's getting closer and closer and closer. Okay. Let's kind of dig a little bit deeper into these 3 examples for a second. The first 2 examples, I got n behaviors that went to infinity or negative infinity, depending on the situation. Would those represent top-heavy or bottom-heavy functions when I take those limits? What do you think? Yeah, so great guesses. So these would represent top-heavy functions. So remember with top-heavy functions, we are going to find that my limit will go to infinity or negative infinity, respectively, depending on the end behavior of that graph, okay? So when I say top-heavy, I'm referring to these 2 on the left here, okay? So these 2 would be top-heavy functions. Now, the one on the right went to 0. What do you think would happen there? Is that top-heavy or bottom-heavy? Yeah, great. That one on the right there is bottom-heavy. And we know that because it approaches 0. Okay. What other information could you guys give me about that last graph I had displayed for you? Anything from previous classes or anything you observe on this graph? Okay, so yeah, that limit as, okay, so you're saying that there's no limit as x approaches 0, or the limit as x approaches 0 doesn't exist, okay? And why is that? What's happening there? Okay, they don't meet. Yeah, there we go, Natalia. There's an asymptote there. So you're referring to the fact that there's that vertical asymptote right here at x equals 0. Okay. Any other asymptotes on this graph? Yeah, awesome. Yeah, good job, Mohammed and Hannah and Tony and Michelle. There is also a horizontal asymptote here. at y equals 0. So let's make the big connection here. We know that the limit as x approached infinity, we called this function h of x equaled 0. And we knew that the limit as x approached negative infinity of h of x equaled 0. We said that this was a bottom-heavy function, and it has a horizontal asymptote at y equals 0. So here's what we can now say. We can say that if I have a limit as x approaches infinity of f of x and it equals L, some number L, then I can also say that y equals L is a horizontal asymptote of that function. Now, I mentioned before that sometimes that limit as x approaches infinity of the function is going to be different than the limit as x approaches negative infinity of that function. So if we end up with another answer like m, then we can also say that y equals m is a horizontal asymptote of f of x, okay? So a couple other important things that I want to mention in this right now before we try finding some horizontal asymptotes ourselves. First, keep in mind how you write a horizontal asymptote. You always have to make sure that you write a horizontal asymptote as y equals some number, okay? So super important in terms of notation there. But the other thing that's super important to remember when you're looking for horizontal asymptotes is that you must find the limit as x approaches positive infinity of the function and the limit as x approaches negative infinity of that function. Yes, they might behave the same sometimes at those ends, but sometimes they're not going to. And we've got to make sure that we investigate both end behaviors to make that determination, okay? So let's see what we can do to tie this all together now. We want to find the horizontal asymptotes of the following function. F of x equals 16 plus x to the fourth all over x squared minus x to the fourth. Because it asks me to find the horizontal asymptote, I immediately should be thinking, ooh, I need to find the limit as x approaches infinity of my function, and I need to find the limit as x approaches negative infinity. So right off the bat, I am going to write my two limits. Okay. Now, let's fill in that f of x for our actual given function. And now, because this is a limit as x approaches infinity, remember, 150 million, Jeff Bezos' net worth versus a couple measly dollars here and there. We only care about the term that grows the fastest in the numerator and the term that grows the fastest in the denominator. So we are just looking at that x to the fourth over negative x to the fourth. So this is one of my situations where the numerator and the denominator, their exponents are equal. And when we simplify this, we are simply going to be looking at the ratio of their coefficients, which would be -1. Boom. All right, let's look in the other direction. Now we have the limit as x approaches negative infinity of f of x. Let's fill in that function. We're taking that limit as x approaches negative infinity. So we are looking at the terms that grow the fastest in the numerator and the denominator. When we do that, we find out that we have exponents that are equal to each other. So again, we're just looking at the ratio of those coefficients, which is going to give us -1. How many horizontal asymptotes am I going to end up with for this function? 1 or 2? What do you think? Yeah, 1. Because in this case, my function approached -1 at infinity and at negative infinity. So after you take these limits, you've got to be really careful to make sure that you answer the question. Find the horizontal asymptotes was the question. We went through and found these beautiful limits. We talked about how the exponents are equal. We got out -1, but we haven't actually answered the question yet. The answer to this question is that there is a horizontal asymptote at y equals -1. So make sure that you answer that question and that you're writing that equation of your horizontal asymptote after you do those limits. All right, here's our next example. Same set of directions. We want to find the horizontal asymptotes, but this time we're going to have the function h of x equals 1 minus x squared all over x cubed minus x plus 1. Try to see if you can work this one out on your own, and let's compare answers. So take a couple of minutes and see what you get when you work this one out yourself. Once you think you've got the answer to this one, go ahead and comment in the chat what you think the horizontal asymptote is. Yeah, looking good. Be super careful. I'm noticing that a couple of you are commenting without putting the y equals, okay? Even though we're just commenting in the chat feature, I know it's casual setting, which is totally cool. But remember that in order for it to actually be a horizontal asymptote, it does have to be written as y equals, and then 0 is the correct answer in this case. So if I take this limit as x approaches infinity of h of x, this particular function ends up being bottom heavy. I'm looking at -x cubed or -x squared over x cubed. That's bottom heavy, so we know that because it's bottom heavy, this is going to go to 0. Same situation is going to happen when I have my function approach negative infinity. Because both of these limits went to 0, I find that, again, I only end up with one horizontal asymptote, and it is happening at y equals 0. All right, I'm going to up the ante on you guys a little bit on this one, okay? This time, I want us to find the horizontal asymptotes on the function. Well, yeah, great, Mohammed. So if it's bottom heavy, you're going to find that it has a horizontal asymptote at y equals 0. So remember, we're going to write that as an equation. But yeah, bottom heavy is going to end up with an asymptote of y equals 0. And we're going to come and circle around and summarize that in a couple slides, but you're absolutely right. All right, so we are looking at the function g of x now, which equals x over the square root of the quantity x squared plus 1. So, just like before, because I'm looking for, okay, what do you mean doesn't it turn even, Sammy? Oh, I think you're asking me about the exponents being equal, okay? Yeah, we're on that page, Sammy. We gotta be, yeah, exactly. We gotta be super careful though about how we take the square root of x squared. So that's a little bit of a side conversation I wanna have with you guys. So because we're looking for horizontal asymptotes, we know right off the bat, okay, I've gotta take the limit as x approaches infinity of g of x, and I have to take that limit as x approaches infinity or negative infinity of g of x, okay? Here's where I have to be super careful though. When I look at the numerator and denominator, I'm looking at x in the numerator, and I'm gonna look at the square root of x squared in the denominator. But here's my big question for you guys. What is the square root of x squared? All right, I have a question for you guys. Is anybody willing to be a guinea pig for me? I need 2 volunteers. If you'll be a volunteer for me, give me a smiley face. Anybody brave enough? All right, Sammy's my first volunteer. Any other takers? All right, Karen, you're my second volunteer. Awesome. Okay, here's the deal. I'm going to give you a number, and Sammy, I want you to square that number and type it in the chat, okay? So let's start out with the number 7. So Sammy, go ahead and square that number for me. Okay, great. Now, Karen, here's your job. Take that answer Sammy just gave, and I want you to take the square root of it. What do you get? Okay, let's do another one. This time I'm going to give the number 3. Sammy, go ahead and square it. Okay, now Karen, take the square root of that. Okay. Let's do another one. This time I'm going to give the number -2. What do you get when you square that, Sammy? Okay, and now Karen, what do you get when you take the square root of 4? Okay, let's do another one. What if I give you the number -4? What do you get when you square it, Sammy? Okay, and now square root that for me, Karen. Okay, so your answers are all correct, okay? From the outside looking in, when I said 7, Karen said 7. When I said 3, Karen said 3. But when I said -2, Karen said +2. And when I said -4, Karen said +4. If somebody were to walk in from the outside and observe that, what do you think they would think we were doing to that number I gave? Not quite, Mohammed. It wouldn't be plus or minus. Yes, exactly. We have to make sure that we use our absolute value. So a common mistake that students make is that they say, oh, the square root of x squared is x. This is not the case, though. The square root of x squared is the absolute value of x, okay? So let's keep that in mind as we move forward with this example, okay? I need to take the limit as x approaches infinity of g of x. And because I'm approaching infinity, I'm worried about that term that's growing the fastest on the top and the bottom. So I'm going to be looking at the limit as x approaches infinity of x over the square root of x squared. But we just had that side conversation that this is really the limit as x approaches infinity of x over the absolute value of x, okay? So, absolute value of x. Let's think about this as a piecewise function for a second. This is x when x is greater than or equal to 0, and it's negative x when x is less than 0. If I am taking my limit as x approaches infinity, the piece of this absolute value function that I'm going to use is going to be x, because x is greater than or equal to 0 as I go to infinity, okay? So I can take this one step further now and say, based on my knowledge of the absolute value function, this is the same as the limit as x approaches infinity, of x over x. And so I don't remember who it was that mentioned it initially, but those exponents are equal. X over x would simplify to 1. So we're looking at that ratio of coefficients as just being equal to 1. Let's do the same exact thing now, though, going to negative infinity. Watch how this works out just a little bit differently. So we are still going to use the approach that the square root of x squared, whoops, I forgot my negative there, is the absolute value of x. Here's why this becomes so important, because now as my x is approaching negative infinity, and actually let me do that in a different color, I am now using the other piece of my piecewise function from the absolute value of x, because negative x is the piece I use when x is less than 0. So if I'm approaching negative infinity, I'm really now looking at the limit as x approaches negative infinity of x over negative x. Exponents are equal there. The ratio of their coefficients is not 1, it's -1. So in this particular problem, I didn't end up with one horizontal asymptote. I'm actually going to have 2 horizontal asymptotes. I end up with horizontal asymptotes at y equals 1 and at y equals -1. Okay. Anybody have questions about that square root of x squared or that absolute value of x? No? Awesome. Good. I'm glad that that helped, Mohammed. Okay, let's go back and talk about those 3 scenarios we came across again, okay? We talked about when it was top heavy that my limit would go to positive or negative infinity, okay? If my limit goes to positive or negative infinity, we are going to find in those instances that there is no horizontal asymptote. We saw bottom heavy. And in my bottom heavy scenario, we said that our limit goes to 0. And in that case, we are going to have a horizontal asymptote at y equals 0. And then we come across a situation where our exponents are equal, or the term in the numerator is growing just as fast as the term in the denominator. And in this case, we said that the limit goes to the ratio of the coefficients. And that's going to lead us to a horizontal asymptote, y equals the ratio of those coefficients. Oops, coefficients. There we go. And that's it, okay? That's really limits at infinity in a nutshell, and also tying it back into end behavior and horizontal asymptotes, okay? I hope that you have enjoyed our time together tonight. I did have some additional examples, but we're 8 minutes over our hour, so maybe I'll squeeze those into another stream that I do in the future. But I want to mention that next week, we're going to have a stream on continuity, Monday, September 16th at 8, and that one's going to be with Megan. There's also going to be a continuity part 2 coming soon, so stay tuned for that date and time. And again, keep in touch at Think Fiveable to stay up to date on what streams we have coming up. I will stick around, so if anybody has any specific questions they want to ask me once everybody's kind of left the chat, let me know. Otherwise, thanks for coming, and I hope to see you at my next stream as well. Great job. Sammy, right now, I'm not scheduled for the BC problems. There's other great streamers that are going to be out there too, doing some of the BC problems. I might eventually be doing that. Was there a specific topic that you were hoping to see for BC? Integration by parts, that's a fun one. I'll make sure that I pass that word along and try to get somebody to do a stream on the integration by parts. Is that something that you're already covering in class? Gotcha. Yeah, so I'll definitely pass that along and see if we can get an integration by part stream sometime in the near future. So hopefully we can get any of that confusion worked out sooner rather than later. So definitely stay tuned to the calculus streams for the Fiveable so that you can see when that one will come up. You're very welcome, Sammy. Anybody else have any questions? All right, if anybody else does end up having questions, feel free to reach out to me. My email address is sfaralock@me.com. Otherwise, have a great evening.